So just a reminder what we've been talking about. We've seen this principle called Gauss's law. Most formal expression of it is the closed integral of E dot n hat dA over a closed surface being equal to the charge inside that closed surface divided by constant epsilon naught. So we were looking last time at some examples of how to apply it to various situations and use it for evaluating electric fields in cases where you have very high symmetry, such as the spherical case that we looked at. We used it to talk about various properties of conductors. It's a more formal way to prove some things about conductors we already knew, like charges only at the surface. We also saw last time that if you have a cavity inside a solid conductor, then there can't be any charge on that surface either, or there can't be any charge on that surface. It can only be on the outer surface, I should say, because of this idea of Gauss's law, meaning that the if the total electric field in the metal is zero, then the charge inside's got to be zero. We also used round-trip potential difference in that proof as well. So there's a more formal proof in the book if you want to take a look at that. And by the way, this thing is called the total flux. Over a closed surface. The book also has some kind of formal proofs about some properties of Gauss's law. One thing that might be confusing at times is why does only the charge on the inside of the surface matter? I mean, for example, if I have charges in space, so I have a Q1 here and a Q2 here, and I happen to pick a surface that only encloses Q2, then I'm looking at the electric field on the surface to calculate the flux, but that electric field, due to superposition, is the net electric field due to all charges in space. It shouldn't matter whether I enclose this charge or not. Q1 is going to be affecting the net electric field here just as much as Q2 is. So why is it the case that only the inside charges on the inside matter? And we can go through some formal reasoning about that, but it's often a bit more useful to take a look at a little simulation here, which I'll bring up. So here's a positive charge, here's a negative charge. Let me bring a positive charge down here. And the way we need to understand this is this is actually a positively charged rod that is coming out of the screen towards us. So this is extending in space in and out of the screen. And since it's a positively charged rod, I can actually draw a surface around it. And again, this line that I'm drawing is actually, you can think of as a surface that's enclosing the rod, okay, ignoring the end caps, but the end caps are essentially infinitely far away. So we're thinking about this path here as being a surface that's extending again into and out of the screen. So we really do have a charge enclosed by a surface. And let me just clear that for a second. We know that the electric field due to a positive charge is pointing away. And so if I draw a surface, what the program is doing is it's breaking this surface up into little pieces and calculating the net flux over each little piece by evaluating the electric field there and multiplying by the area, the surface area, okay, E dot n hat times delta A. And a positive flux is represented by sort of these little yellow rectangles. It looks kind of like a fuzziness or something going around the outer edge of this surface. And graphically, the program is indicating a positive flux by these yellow rectangles extending out toward the outside of the surface. Okay. It adds up all those positive fluxes, and then it just uses Gauss's law, divides by, or actually multiplies by epsilon naught, and we get a charge. And in these units, the charge is +1. Okay, So there's a +1 charge in here. It doesn't matter where the charge is, because if I drag the charge over to one side, what happens? It's still +1. What happened to the flux over on this side? Got bigger, but what happened to the flux everywhere else? Got smaller, okay? So the total flux stays the same, and the total charge enclosed stays at +1. So we still have the same charge inside, and Gauss's law is still computing the same charge inside, because if the flux gets bigger here, it gets smaller elsewhere, okay? So fact number one is it doesn't matter where this charge is. As long as it's enclosed, we get the total flux giving us information about the total charge. Now, what happens when I bring this charge outside? Okay, it's getting really positive here, but now what happened? What's the flux on this side now? It's negative, isn't it? And that's represented by these rectangles now kind of pointing into the interior of the surface. So wherever you see these rectangles pointing into the interior, we have a negative flux. Everywhere else, what do we have? Positive, right? So I've had this really big negative flux over a smallish area with really with a smallish positive flux, but it's over a larger area, right? So we're just adding up more and more of these fluxes over more and more area. And so it sums up to 0, okay? The direction of the electric field flipped directions over on this side of the surface, and so we get a negative flux, but it stayed the same everywhere else on the rest of that surface, mostly. And so we still got a positive flux. So here, charges inside, net flux is positive. Charges outside, then we get some negative here, positive elsewhere, adds up to 0, okay? Again, I can choose any surface that I want. Let me clear this and choose a smaller area. Smaller area, but bigger field, right? So again, E times A stays the same, essentially. We get a bigger positive flux, but the same charge inside. Or I could pick a very large area. Small electric field is over this surface, but just lots and lots of area. So we see that over each little segment of area, there's a small flux, but when you add them all up, we get the same amount of charge on the inside. Okay, and again, it doesn't matter where I place that charge. It's still the same. Shape doesn't matter. I could choose a kind of a crazy shape here. And there's all kind of weird things going on here, right? But we have some cases where along some parts of the surface it's actually might even be negative. In fact, let's see, can we find a place? Yeah, kind of right here. I don't know if you can see it. That part of that flux is actually negative because it's graphically it's in toward the center. Everywhere else it seems to be positive. A little bit of negative here. But when you add, in fact, let me make a simpler but still complicated shape to kind of show this. Let's put this one little S turn in it. Okay. So I have positive flux. So here's some positive flux, and then here's some negative flux, but then here's some positive flux again, right? So when I add these together, I get some cancellation, and it doesn't really matter that there is this S turn in here because I'm not getting more positive flux by this S turn. I'm getting some negative, and so that's leading to a cancellation effect, and I get the same amount of charge inside. So it gives me the same result as if there wasn't any S turn in there at all, because that positive part and negative part cancel out and just leaves me left over with just one positive contribution, essentially. Okay. So the shape of the surface doesn't matter. The placement of the charge inside the surface doesn't matter. The size of the surface doesn't matter as long as it's a closed surface. What about charges on the outside? So here's our positive charge. Let me bring another positive charge nearby. And you see that did change the sort of distribution of flux. Let me put some electric field vectors here just to show a bit more clearly. what's going on with the electric field. So I'm just plotting electric field at various observation locations. And this is the net electric field due to all charges. And I can move this charge closer, and that's going to, of course, affect the net electric field at these locations. But you see that the total flux over the surface stays the same, because as I move this closer, I've got now negative flux here, but what happened everywhere else? It got bigger, right? It got more positive. So there's a compensation going on because the field everywhere is being affected. I'm changing, the sign of the flux here, but it's compensating by getting larger everywhere else on the surface. So if I move that charge away, the flux again changes locally, but when I add it all up, it still gives me total flux equal to the charge inside. Bring that charge outside and suddenly it goes to zero, but as long as that one charge stays inside, then there is this compensation going on, and I can even move this charge elsewhere. It's changing, again, the field at various locations, changing the flux over various bits of this total surface, but overall, when I add it all up, I get the same total flux. Okay, and I can do this with negative charges. Okay, same sort of thing. I can bring as many charges in here as I want, and you can see how the flux on each side keeps getting bigger as I add more and more charges. But because it's getting more negative here, it's just getting more positive on the other side, and so the sum stays the same. Okay? So that's the basic idea. I'm not going to go through the formal mathematics of it, but if you're curious, you can take a look at the book. But you can kind of see graphically what's going on. That, again, the shape of the surface doesn't matter as long as it's a closed surface. The placement of the charge inside doesn't matter. And charges on the outside, no matter where they are, don't matter. Okay, it's just the total flux of the closed surface tells you about the charge inside. Okay? Total electric flux over a closed surface is going to give you the charge inside divided by epsilon 0. Well, I could do the same thing with magnetic fields, right? I could calculate the magnetic field over a closed surface. So if we have a box, for example, again, an imaginary box, and if we were looking at B instead of E, there might be magnetic field here, and then magnetic field on the bottom surface, okay, or something like that, right? And so I can do the same thing. I can calculate B dot n hat dA, so magnetic flux phi sub m would be B dot n hat times a area element, okay, flux over closed surface. Once again, reminder that when we're talking about a closed surface, these n hats are always defined to be pointing toward the outside of that closed surface. And then I can sum up all those B dot n hat dAs, so summing up all the fluxes, or doing continuous integral, just summation of B dot n hat dA, would give me what? Does anybody know what the result would have to be? Why 0? Okay, you don't want to say all the magnetic fields would cancel each other. Fluxes would cancel each other out. I guess the question is, okay, so this is what this is telling you, right? The magnetic fluxes over a closed surface are summing up to be equal to 0. Now, for electric fields, when you sum up all the electric fluxes, they tell you about electric charge. So let's make an analogy. You sum up all the magnetic fluxes, they tell you about what? What would be the magnetic analog of an electric charge? We've heard this term before. I'm just seeing if anybody remembers. A magnetic blank. That's been a while. Magnetic charge or a magnetic monopole, right? Let's look at a bar magnet again. Okay, you have a north pole and a south pole. And at this point, the magnetic field is pointing in what direction? To the right, okay. And it kind of points to the right along here. And you have magnetic fields pointing in that direction. And at the south pole, it's pointing towards the south pole, right? So you get this dipole pattern of magnetic field. And if I placed a closed surface, I placed this bar magnet in a box, okay, you can probably kind of see that, yeah, the total flux would have to be 0, right? Because you're getting a positive contribution on this side, a negative contribution on this side, mostly 0 everywhere else because you might have a little bit of positive here but some negative here, and then 0 when it's pointing in that direction. So when you add it all up, it gives you 0, okay? And the net monopole, or the net magnetic charge, so to speak, is 0 because you have both a north pole and a south pole. What would we have to have in order to have a net positive or net negative contribution? Capacitor? Capacitor is that's an electric field, right? So we're talking about magnetic fields here. A monopole. So if I have an isolated north pole and I put that in a box, what would the pattern of magnetic field look like if this could exist? It would look like a positive charge, right? It would look like an analog to a positive charge. You'd have a magnetic field pointing out away from that isolated north pole. And if I added up all the flux over this closed surface, over this box surrounding this isolated north pole, what would the sign be? Give you a positive, right? Give you a positive because the field's pointing toward the outside. Has anybody ever seen this? Have you guys seen it before? I don't know. Anybody seen a magnetic monopole lately? No, I haven't seen one lately either. Now, it turns out that, as far as we can tell, no one has ever actually seen or observed a magnetic monopole in an experimental setting. People have been looking for them for a long time, but so far, no such luck. So it seems to be the case that there are no isolated magnetic charges or isolated north or south poles that would create either a net positive or a net negative flux. The only thing we can have are dipole situations, or, if you have a current, what would a current give you? Here's a wire carrying a current. You have magnetic field coming out at the top, field going in at the bottom. You could imagine surrounding this wire with a surface, like a cylindrical surface, and everywhere you'd find the magnetic field, if this cylindrical surface was symmetric, right? The magnetic field being parallel to the surface, right? At the top, it's parallel to the surface. At the bottom, it's parallel to the surface. On the front side, it would be pointing down, parallel to the surface. And all of that would add up to a net flux of 0, right? So no matter what we do, no matter what kind of patterns of field we've looked at, magnetic fields, it's always going to be the case that the total flux over a closed surface is equal to 0. So this is Gauss's law for magnetism. Magnetic version, I guess you could say. And it's just another way of expressing the fact that no one's ever observed or measured a magnetic monopole.